Alright, welcome to Lesson 7. We're going to pick up where we left off with Part 1 of the fundamental theorem of calculus. We're going to discuss a little more what's meant by antiderivative, and we're going to state all the consequences of this part of the fundamental theorem. And then we're going to move on and derive the second part of the fundamental theorem of calculus and apply that particular part to evaluate definite integrals. So very important, make sure you take your time with this one.
All right, go ahead and work through problems 1 through 4 on your own. Make the discovery and then go ahead and press play, and we'll discuss its ramifications. Okay, so first off, I want to find a function, capital F, whose derivative is lowercase f, which is 3x squared minus 2x. So here you want to think back to your derivative rules, and remember, of course, that you can take the derivative of a function term by term, right? So if you have capital F and you have two terms, one term minus a second term, let's just write that out here, one term minus a second term, then when you take the derivative of each term, they better match up with lowercase f. So the derivative of this first term had better be 3x squared. So thinking back to your power rules, you're thinking about a function whose derivative would be 3x squared, and that, of course, is x cubed. And then the next one, the derivative of this term, had better be 2x. And again, the power rule allows you to figure out that that will be x squared. Okay? So to check that I'm correct, I'll quickly take the derivative of this. And sure enough, the derivative of x cubed is 3x squared minus the derivative of x squared, which is 2x. Okay, so that worked out. Now, in question 2, I want to find the derivative of capital G. So I look at capital G here, and I'm going to go ahead and differentiate again term by term. And when I do that, I notice that I get 3x squared minus 2x plus 0. Well, plus 0 is meaningless here, so I end up with capital G prime being equal to 3x squared minus 2x. And what do I notice? I notice that this is the exact same derivative as f prime of x, right? These are the same function. However, the functions that I took the derivative of, capital F and capital G, are different. What do they differ by? Well, they differ by a constant, right? One of them has a constant term. And so, because the derivative of a constant is 0, this is going to be meaningless when I consider the rate at which each is changing. So their derivatives can be the same, even though the original functions are slightly different. So with this in mind, we now think about, okay, how many possible functions could we make whose derivative would be 3x squared minus 2x? We've just seen 2 examples, and this should lead us to understand that we could create as many examples as we want. All we'd have to do is change the constant term. So this leads us to conclude that we could write infinitely many of these functions whose derivative would be 3x squared minus 2x. And so this leads us to want to write the general form. What will every one of those functions look like? Well, we know 2 components that each must have, right? If we look at these 2, capital F and capital G, they each have an x cubed minus x squared. Right? Taking the derivative of those 2 will give me 3x squared minus 2x. But the part I can change is the constant term. So every one of these functions will be x cubed minus x squared, and then it can be plus any number, right? It could be plus a negative number, which would give me minus some value, or it could be plus a positive number, any constant term I want. And so I can represent that with plus c. And notice there are infinitely many ways that I can write this function given a choice of my constant term c. All right, so let's name this process. If lowercase f is the derivative of capital F, which means I take the derivative of this function and I get this function, then capital F is the what of lowercase f, meaning what process would I have to do to lowercase f to end up with this function? Well, think about the process that we took. We didn't take a derivative, we went a step the opposite direction. We thought about a function that you would take the derivative of, which is what's called antiderivative or anti-differentiation. So capital F is the antiderivative of lowercase f of x. Okay, so let's define an antiderivative. So a function capital F is the antiderivative of a function lowercase f if capital F prime of x is equal to lowercase f of x for all x in the domain. The process of finding an antiderivative is, of course, called antidifferentiation. So, as we just discovered, if f has an antiderivative, if lowercase f has an antiderivative, then there are going to be infinitely many possible antiderivatives of lowercase f. And all of them are going to only be different by a constant term. So that's why we write that plus c, because guess what? It doesn't matter what that c value is. When we take the derivative of a constant, it goes to 0. So the other pieces are the only parts that are going to stick around. That constant is going to disappear. So at this point, we just need to go ahead and start taking the antiderivative, or finding the antiderivatives of some functions. What we'll need, of course, is our derivative rules. So you might want to dig those up in your study guide or in your notes. Take a quick glance back over them, and then go ahead and try to find all of the antiderivatives of each of these functions. Remember, you can use c to represent any constant value. Okay, so starting with lowercase f of x, and we represent the antiderivative with the capital letter. So capital F of x is going to need to be 5x, because the derivative of 5x is 5. But we want to include all the possibilities, so plus c, where c is any constant value. So, all right, moving on to lowercase g. So the antiderivative, capital G of x, is going to need to be a function that when I take the derivative of it, I get x to the first power. Well, the power rule tells me when I take the derivative of a power function that the exponent will decrease by 1. So I need x to the second power. However, if I took the derivative of this, I would get 2x. So I need to make sure that there's a coefficient that when I multiply by 2 just gives me 1. Well, that coefficient is going to be 1/2, or we could write x squared over 2. Now remember, I can have any constant, because when I take the derivative of that constant, I'm going to get 0. So I'll have x squared over 2 plus c. Okay, so now we need a function whose derivative will be sine of x. So going back to our trigonometric functions, we're going to look for a function whose derivative is going to be similar to sine of x. And when you're looking through, you'll notice that the derivative of cosine of x is sine of x, but negative. So let's start there. Let's say, okay, we had cosine x. Well, the derivative of that is going to be negative sine of x, and we don't have the negative here. So we need to have a negative out front, so that when we take the derivative of negative cosine of x, we factor out the negative, and we'll have negative sine of x, which would be exactly what we want, and we can, of course, add a constant c. So that will be my antiderivative of sine of x. So hopefully all this work with the antiderivative helps to clarify why the first part of the fundamental theorem is called the antiderivative part. So take a second to refamiliarize yourself with the first part of the fundamental theorem, and then we'll discuss a little bit more about the consequences that come from it and why the antiderivative piece is so important. So the first thing that we should notice is that if we're given a continuous function, then that continuous function is the derivative of some other function. And we see that very clearly here. When we defined capital F of x to be the accumulator, and we took the derivative of that, we ended up with simply lowercase f of x, which means that lowercase f of x is the derivative of that accumulator function. So notice also that this means that every continuous function, lowercase f, has an antiderivative. Remember, the antiderivative of lowercase f will be the function whose derivative equals lowercase f of x. And that's exactly what we constructed here. The accumulator function, the derivative of the accumulator function, is going to be equal to lowercase f of x. So the statement here is very powerful. Not only does it say that every continuous function will have an antiderivative, but it also is helping us to construct that antiderivative using the accumulator function. Notice, of course, that when we talked about antiderivatives, we mentioned how you can have infinitely many. And the way that would happen is that we can choose any constant and add any constant to our accumulation. And when we take the derivative, that constant would go to 0. So we'll still end up with the same derivative. So it's important to note here that this theorem states that one of the antiderivatives that lowercase f will have is the accumulator function. And in other words, where we have a constant term that is 0, okay? But we recognize that we could have any constant term there. All right, the processes of differentiation and integration are inverses of one another. And we can see this very clearly here. I'm applying the integration to my function f of t. And when I take the derivative of that integration, I'm finding that the rate at which it's changing is simply f of x. So they're essentially undoing one another. And because of this, we need to have a way for recognizing when we're differentiating, which we have already. This represents that I'm taking the derivative of f of x. Well, what if I want to take the antiderivative? That's what we call integration. And of course, would look like this. So this says, find the antiderivative of f of x with respect to x. And this says, take the derivative of f of x with respect to x. So now we have both processes. We can go either way we want, and we have a theorem that tells us that if we have a continuous function, we know for a fact that it's going to have an antiderivative. And more importantly, we can actually define one of those antiderivatives using the accumulator function. So with that being said, now let's go and spend a little more time talking about how antiderivatives will be portrayed going forward. So since we mentioned that differentiation and integration are inverse operations, it makes sense that when we think about the antiderivative, what we're really thinking about is an integral. And so this is what's called the indefinite integral, and it's what represents taking the antiderivative of a function. So the family of all antiderivatives of a function, lowercase f of x, is the indefinite integral of f with respect to x, which is denoted in this way. So the way I would read this is the indefinite integral of f with respect to x. And here's how we would write that. So if capital F is any function such that capital F prime of x is equal to lowercase f of x, and all that means is that capital F is an antiderivative of lowercase f, then the indefinite integral of f with respect to x is simply that antiderivative, capital F, plus c, where c is an arbitrary constant, can be any constant value, and that's called the constant of integration. And we've spoken about this before. Because when we take the derivative of a constant, it goes to 0, what we'd be left with, no matter what the constant is when we take the derivative, is simply going to be lowercase f. Okay? So when I'm taking the indefinite integral of some function, I need to make sure that I include this constant of integration, because I can have it there. It can be anything I want. It does not change the fact that when I take the derivative of this, I'm going to end up with lowercase f of x. So this is actually a pretty simple process, just a little more formally defined than we had it before for how to take the antiderivative of a function. So let's go ahead and get a little bit of practice here. Go ahead and work through both these problems to find the indefinite integrals below. Okay, so since each of these is an indefinite integral, what I'm doing is finding what's called the family of antiderivatives. So I want to find a function whose derivative will be x. And using the power rule, I know that that's going to be x squared, but I have to have it over 2 so that when I take the derivative of this, I get simply x. And I can have any constant that I want added on, because when I take the derivative of the constant, I'll get 0. Similarly, over here, I need something that when I take the derivative of it will be e to the t. Luckily, the derivative of e to the t is e to the t. So this is simply going to be e to the t plus c. And so what each of these represents are the way that every single antiderivative of this function will look. All that will change is the constant that I add on at the end. And we'll see that these constants have quite a bit of meaning in real life. And just to give you kind of a way to think about it, imagine that you're taking the integral of a velocity function. So that would mean that you're coming up with the antiderivative of velocity, which is, of course, position. But your position function has to have an initial value, right? So it needs to start somewhere. And so that's where that constant of integration can come into play. All right, now with all of this that we have, we're ready to tackle the second part of the fundamental theorem of calculus. So let's take a look. So just like the first part of the fundamental theorem of calculus, Newton and Leibniz came up with the second part by noticing a pattern. Right? So we looked at the geometric interpretation of the first part of the fundamental theorem of calculus. And for the second part, they were noticing a pattern as well. And so what we're going to do is discover that pattern and use that pattern to make a hypothesis for what the second part of the fundamental theorem of calculus will be. So to set us up, let's imagine that we were trying to figure out how to evaluate the integral from a to b of some function f of t dt. And we were tired of using the interpretation of the areas between the curve that were above minus the areas between the curve and the x-axis that were below. So we're trying to discover a new way to do this. Go ahead and follow the directions in 1 through 5 using either one of these integrals here, definite integrals, and see if you can figure it out for yourself. Okay, so I'm going to go ahead and go through this having chosen the first definite integral. And notice that when I want to evaluate this definite integral, since it's a constant, the integral of a constant function, that's rather easy to do. And representing it graphically, I know that I'm just taking the area of that rectangle, which will be 7 times 10, or 70. So now I'm looking for an antiderivative of my function 7. And I'm going to call this antiderivative uppercase f of x. And I know, of course, that if I take the indefinite integral of 7 with respect to x, that's finding all of the antiderivatives of that function in terms of x. And so this is going to be 7x plus c, where c is any constant. And so I can choose any function of this form. And you probably just chose 7x, but I'm going to go ahead and choose a constant value. I'm going to use 7x plus 2. All right, now I want to evaluate my function capital F at the lower limit of our integral and at the upper limit of our integral. In other words, we want to find f, capital F at a and capital F at b. So I notice that my lower limit is 1 and my upper limit is 11. So capital F evaluated at the lower limit of 1 is going to be 7 times 1 plus 2, which is 9. And capital F evaluated at 11 will be 7 times 11, 77, plus 2, which is 79. Now, I want to notice a relationship between the answer that we got evaluating our definite integral in part 1 and the answer that we got here in part 3. What you might notice is that the difference between capital F evaluated at 11 and capital F evaluated at 1, the limits of my integration, is going to be exactly equal to the value of my definite integral. In other words, what I'm really noticing here is that it appears that my integral from 1 to 11 of 7 dt is simply equal to capital F, the antiderivative of 7 evaluated at 11, minus capital F evaluated at 1, which was simply 79 minus 9, or 70. And what's interesting to notice here is that even if you chose a different antiderivative, you would have found the same relationship. So based on what we've discovered here in this one example, and if you did example 2, you discovered the same relationship, how might we hypothesize that you would evaluate the definite integral from a to b of f of t dt? Well, it doesn't take a whole lot of rocket science to figure out what our hypothesis is. If we have the definite integral from a to b of lowercase f of t dt, it appears as though the value of this definite integral can be found using any antiderivative, capital F, evaluating it at the upper limit, and subtracting capital F evaluated at the lower limit, where capital F simply represents any antiderivative of my function lowercase f of t. Now, notice for a second how incredibly simple this equation looks for something that has seemed so hard to calculate, the definite integral from a to b of any function f of t dt. So if this happens to be true, if we can prove that this is true for any continuous function f, this would be quite an incredible result, one that would be so incredible that it might be deserving of the name fundamental theorem of calculus. So let's take a look and see if this is in fact what Leibniz and Newton also discovered. Sure enough, our hypothesis was the same one that Newton and Leibniz had, and this led them to the discovery of the second part of the fundamental theorem of calculus, also known as the integral evaluation part. And here's what it states. If lowercase f is continuous at every point on the closed interval from a to b, and if capital F is any antiderivative of lowercase f on that closed interval, then the definite integral from a to b of lowercase f of x dx is equal to capital F evaluated at b minus capital F at a. And this part of the fundamental theorem is also sometimes referred to as the integral evaluation theorem because it does just that. Okay, so take a second, make sure you've copied this down accurately, and think about what the consequences are of this theorem. So the consequence of this second part is simple but incredibly important. What it says is that any definite integral of a continuous function, lowercase f, can be found easily if you can find an antiderivative of that function. Now, remember that the first part of our fundamental theorem said that any one of its consequences, I should state, is that any continuous function will have an antiderivative. That was the role that the accumulator function played. And that means that anytime we are taking the definite integral of a continuous function, there will be an antiderivative. It just comes down to, can we find it easily? And then once we've found it, we can evaluate it at the upper limit and at the lower limit of integration, take the difference between the two, and that is the value of our definite integral. Now, to help you understand just how important and powerful this theorem is, let's consider another consequence. To help you understand why this would be thought of as a consequence, imagine that you are one of the founders of calculus. You're discovering calculus. And you have been calculating, or rather I should say approximating, the value of these definite integrals using Riemann sum approximations to find the signed area between the curve and the x-axis. And you want to be precise, so you're using lots of subintervals, and so they're very small, and the calculation is very tedious, and you don't have a calculator, so it takes you, lots and lots of time, hours and hours and hours. For really complex ones, I mean, we're talking serious time here. And all of a sudden, you notice this pattern with respect to the antiderivative of this continuous function. And in fact, you're able to prove that this is the case, that any antiderivative of our function, lowercase f, evaluated at the upper limit minus this antiderivative evaluated at the lower limit will give you not just an approximation, but the exact value of this definite integral. So all of a sudden, what has been taking you days and days and days has been trimmed down to a couple of minutes. And I'm not saying that this proves it, but if you discovered this, you might be wondering, is there a God up there? Because this is almost too easy to possibly be true. So, to make sure that you believe it, we're going to go ahead and prove it in just a second. Before we prove anything, it's important to talk a little notation here. The key piece to actually evaluating this definite integral using the theorem is going to be finding an antiderivative. And since when we're finding an antiderivative, as we have done previously in this lesson, we're going to find the antiderivative in terms of x, right? It's going to have a variable involved. And then only after we have it in terms of x are we going to evaluate it at b and a. And so we want to be able to write this intermediate step where we show that we have the antiderivative and that we're going to evaluate it at b and at a and take the difference of the two. So there's a couple ways to write it. The first is like this. I'll write out my function, capital F of x, whatever it is, and then to show that I'm going to evaluate it at b and at a and take the difference, I write that little bracket with the limits on the upper and lower part of the bracket. I can also represent it like this, where I have the bracket on the left side as well. So this is going to be actually the intermediate step. I'm going to find the antiderivative and write it that what I plan to do with it is evaluate it at b and a and take the difference. And then after I've written it like that, I can then have another step where I actually evaluate our capital F of x at b. I'll have that here, and then subtract capital F evaluated at a and simplify as necessary. So with that being said, let's prove this quickly so that we can apply it knowing we're doing the right thing. So to prove the fundamental theorem of calculus, there are two parts, of course, and the first part, which we've already looked at, we did a geometric proof, and I put that in quotes because it's not a rigorous proof, in that we left a couple of things out. We kind of glossed over them. And so we're going to prove it more rigorously later once we've learned a key piece that will allow us to get there. But if you wanted to prove it to your friends or to yourself, you'd want to go back and use the geometric proof, right? That's what really allows your mind to believe that what you're reading is correct. Okay, so now we're going to go ahead and prove part 2. Here's the statement of the theorem right here. I'm going to move it up a little bit. And we notice that the preconditions for this theorem are that f has to be continuous at every point in the closed interval, and capital F is going to represent any antiderivative, and any is important, of this lowercase f of x. And then what we're going to look to show is that capital F of b minus capital F of a is in fact the definite integral from a to b of lowercase f of x dx. So we start off and we are going to assume that lowercase f is continuous, and so that means if we look at part 1 of the fundamental theorem that any continuous function is going to have an antiderivative, and more so that we can write an antiderivative of lowercase f as the accumulator function, which is defined as the definite integral from a to x of f of t dt, and we'll name that particular antiderivative capital G of x. Now, notice our theorem states that this should be true for any antiderivative, which is known as capital F. This is a specific antiderivative, and so we need to represent capital F in some way. Now, we know that capital F is also an antiderivative of lowercase f, just as capital G is. And since they are antiderivatives of the same function, that means when we take the derivative of capital G and capital F, they both turn into the same thing. So the only way they could be different from each other is by a constant. And so that allows us to write capital F in this way. Quite simply, that if f is any, I would underline that, antiderivative of lowercase f, then capital F will only differ from G by a constant, and thus capital F of x is equal to capital G of x plus c for some constant c. Could be anything. Now, I have a way to represent capital F, so now I can write this statement here, capital F of b minus capital F of a. And writing it out formally now, capital F of b minus capital F of a, using how we just defined it, that's going to be capital G of b plus c, that represents capital F of b, and capital F of a is simply going to be capital G evaluated at a plus some constant c. And so now, let's go ahead and simplify this statement a little bit. Since we have c minus c, we're going to end up with capital G of b minus capital G of a. Looking back at our definition of capital G, we see that this is simply the accumulator function. So we now evaluate our accumulator function at B and at A. And this is easy enough to do. All that involves is changing our upper limit of integration, and hopefully now you can see how this simplifies. Because when I take the definite integral from A to A, I'm accumulating absolutely nothing. And so this has a value of 0, which leaves me with what exactly I was trying to get, which was the definite integral from A to B of f of t dt. And what was this equivalent to? This was equivalent to capital F of B minus capital F of A, where capital F was any antiderivative of my continuous function, lowercase f. So I have shown now that this statement here is exactly equivalent to this statement of the definite integral. I have finished my proof. So now it's time to go ahead and apply our fundamental theorem of calculus, and this will hopefully show you just how incredibly powerful and useful it is. All right, we want to evaluate this definite integral. I want you to try it on your own first. It might look awful, you might feel awkward. That's okay. Have your fundamental theorem of calculus next to you and try and apply it, making sense of each step as you go along the way, and then we'll take a look at it together. All right, if I look at my fundamental theorem, I can see I need to find the antiderivative of this function here. So if you haven't already, go ahead and find one. All right, so I wanted to show a little bit of work, and you might be able to do this in your head to find the antiderivative of x cubed plus 1, but just to show the antiderivative family of x cubed plus 1, use the definite integral to represent that I'm finding that with respect to x. And that's going to be x to the fourth over 4 plus x plus any constant c. Now, to make my life easier, I'm obviously going to choose that my constant be 0. That's the most simple antiderivative. And so my capital F of x will be this right here. So now I can evaluate my definite integral. Capital F of x is x to the fourth over 4 plus x. I'm going to evaluate at 3 and at -1, and I am going to take the difference between the two, so I can show that here. First, I'm going to evaluate at 3. I'm going to put that in parentheses. I can do a little bit of work as I go. 3 to the fourth is 81 over 4 plus 3 minus, in parentheses now, -1 to the fourth is +1, so I have 1/4 plus 1. And now to simplify, I simply want to take advantage of the construction here, so I'm going to distribute the negative. I will have 81/4 minus 1/4, and then 3 minus 1. So we're going to have 80/4 plus 2, and when you go ahead and divide 80 by 4, you're going to get 22, and plus 2 is going to give you 24. So this is the value of my definite integral. All right, let's go ahead and evaluate one more. This looks a little bit more tricky, but I promise you, just look at it carefully. It's actually quite simple. All right, so first we have to find an antiderivative of our function, lowercase f. And this is probably where you're like, what do I do? Do I take the derivative of this first? And no, absolutely not. Because think about what happens when you take the antiderivative of the derivative. Let's write it out just to be really sure. Okay, hopefully you can see it now. I'm taking the antiderivative of the derivative. These are inverse operations. So I'm left, of course, with only cosine t squared. And if you want any more affirmation, remember that the antiderivative is going to be the function that when I take the derivative of it, I will get this. So that has to be cosine of t squared. And of course, I can add any constant I want, so I could say plus c, but when we're using any, we'll just go ahead and use a c value of 0. So my capital F is going to be cosine of t squared, and this allows me to apply my fundamental theorem. I'm going to take cosine of t squared, and I'm going to evaluate at 3 and at 0 and subtract the 2. So I'll have cosine of 3 squared, which is 9, and minus cosine of 0, which is 1. And so this is the value of my definite integral. If you want to go ahead and calculate this exactly, feel free. Just make sure your calculator is in radians. All right, at this point, go ahead and move on to the homework. Make sure to have your fundamental theorem of calculus handy so that you are able to apply it correctly.